So, in the previous video, we saw that if we have a force that is being displaced in a tiny amount called dr, in that case we can define the scalar work du to be vector of the force dot product by vector of displacement, and that is f dr cosine of theta angle between them. So that is the infinitesimal form of defining work. Now the question is, what happens if the displacement is not small? For instance, if we want to go from one point to another, when the displacement is big, and likely during the displacement, force also changes. Both its magnitude and direction may change. How do we define work in the longer finite displacements? You probably can already guess why I wrote it as du. And the answer is because we are dealing with a scalar function. Essentially, total work from one point to another is going to be the summation of all these little quantities. Or in integral form, it is the integral of du as you go from point 1 to point 2. But how does that integral looks like? So to see that, let me draw this again. I have a beginning and end of a motion going from point 1 to point 2. And somewhere along the way, I have my force like this, and I'm moving in this direction. So if you remember, at this instant that I have drawn, I have du is f dot dr. Call this dr. But note that I'm moving along a path. So as I move, if I am at path coordinate s1 and I'm going to path coordinate s2, this quantity f dot dr, I can write it as size of f times the, let's do this, cosine of angle. So this is the component of f. This is f cosine of theta. And then multiply that by the amount of displacement along the path called ds. So always essentially finding the tangential component of the force, multiplying it by the displacement along the path. Oops, where does this happen? My iPad always does that. This is du, and when we have that, finding the integral of that total work from point 1 to 2 is going to be from S1 to S2 f cosine of theta ds. And that is how you can calculate the amount of work in a non-finite. Somebody knocked on my door. That's fine. I lost track of what I was saying. Yeah, that's how you calculate the amount of work from one point to another. Well, like any other general form, it is kind of harder to visualize. So let's look at one case that this is something we can more easily calculate, and that is when what is inside this integral, what we are integrating, is a constant value. That happens quite a lot. So if f cosine of theta is constant, and when does that happen? A few examples are whenever you are pushing on a particle, if your force is constant and the angle remains always constant, that is one of the cases that this integral is easy to calculate from some S1 to S2. Or your path doesn't need to be straight, as long as always the angle remains the same. Again, this f times cosine of theta remains constant. Let me see, what is a good example? Yeah, this could be a possible example, not a good one, but nonetheless, you have a tube filled with some liquid, you have some particle inside at an angle. Always the force that is pushing it is going to be same amount and at the same angle. So it is going to always be like that. But anyways, if f times cosine of theta is constant, you can take the integral u from 1 to 2 becomes f cosine of theta from S2 minus S1. And that is the amount of work done along a non-negligible displacement. So yeah, I think that is all I wanted to say, actually. Let me see. Yeah, I don't have anything else, actually. So to summarize, to find the work in a finite displacement, non-negligible displacement, you need to take integral, and we'll see a lot of conditions that this integral is well behaved. The simplest one is when f times cosine of theta is constant. That doesn't happen that often. It happens sometimes. Well, gravity is a good example. But other than that, oh yes, I could use gravity. No, I couldn't. Anyways, we'll see a few other examples when this value is not constant, but they are in good forms that we can take the integral. So I'll see you then in other videos with a few other examples.